Okay, last class we started working on digital signal processing. Today's class will just continue working on digital signal processing. So in the last class, we looked at this sort of famous low pass or high pass RC filter. So that's one that you first met in analog electrical circuits, and it's one that we could implement in digital circuits. And so we examined how to implement the RC circuit in digital signal processing. We also talked about how you characterize, or how you can characterize filters, either analog or digital filters, by either specifying impulse responses, step responses, or frequency responses. So in today's class, I want to sort of expand the horizon of filtering in the digital domain. So I want to talk about digital filtering in the time domain. I want to talk a bit about digital filtering in the frequency domain, and I wanted to introduce some digital filters that are commonly used. There's a few of them that I mentioned. So there's a Hahn filter and a Hamming filter. Those are filters, the low pass filters that have high rejection, high attenuation of frequencies above the frequency cutoff. And then I want to talk about the names are brick wall filter, sort of carpet cleaning filter, which are types of filters that are applied in the frequency domain rather than the time domain. And those types of filters have some interesting characteristics when you compare them to the filters in the time domain. Okay, so I just wanted to, in context, just remind you that a couple of slides from the last class related to the low pass RC filter. So basically we sketched out a RC filter electrical circuit, and we used Kirchhoff's rules to write down the differential equation describing the voltages at the input and output of that RC circuit. And then we just turned that into, we kind of morphed it into a difference equation. And the difference equation that we got is over here on the right-hand side. And this equation tells us how to process a digital signal, how to apply a low-pass RC filter to a digital signal. And it simply says that if you want to calculate the ith output sample of your digital signal, you would calculate it from this combination of the ith input sample and the previous I-1 output cycle. So you combine that input cycle and that output cycle together to make the next output cycle. And so that's just a little recursion relation that you can apply to any digital signal to filter that digital signal in a way that mirrors or represents what an RC analog filter would do. And these were the three ways that you could characterize that filter. So upstairs here is characterization in terms of an impulse response. Downstairs on the left here, characterization in terms of what we call step response. And over here on the bottom right, characterization in terms of frequency response. So when we characterize a filter based on impulse response, we imagine applying at the input of the filter a sharp pulse, a pulse spike or a delta function spike, and then we look at the output. And so in magenta here is the impulse that we've applied to the input of the low-pass RC filter. And in green here is the output that you get from the impulse of the RC filter. And so you see that in the case of the low-pass filter, the output has some memory of the input impulse pulse. And it has a time constant that is the time constant of the RC circuit. And in this little example, I had a 10-second time constant. So another way that you can characterize the particular filter is with its response to a step function. So, and in this case, I apply a step function in magenta here to the input of the filter. So it goes from 0 to 1 volts, 500 seconds later, 1 volt to 0 volts, and then it's at 0 volts to 1,000 seconds. So that's the input. And then in green here is the resulting output. And so again, you see that the output has some kind of memory of the input. It takes it time to reach the 1 volt after the input has been switched to 1 volt. It takes time to reach 0 volts after the input has been switched to 0 volts. And those time scales are, again, that 10-second time constant of the filter. And then finally, you could describe the filter with its frequency response. That's what's in this this plot here, over here on the bottom right. So on the axis this time is frequency in hertz, and on the vertical axis is the gain of the filter. So this is the amplitude of the output divided by the amplitude of the input. Imagining that you've applied a sinusoidal signal to the input and you're getting a sinusoidal signal out of the input, out of the output. So it's the ratio of those two sinusoidal signals amplitudes. And that gain depends on the frequency of the input and the output. This is a low-pass filter, so the gain is 1 at low frequencies. This is a low-pass filter, so the gain approaches 0 at very high frequencies. Again, you see that this has a sort of time constant to it. The time constant is 10 seconds, or as a frequency, it's 0.1 hertz. And so that's the sort of scale of the frequency response of this low-pass filter. And so this is a way that we can characterize not just low-pass RC filters, but any type of filter, the digital filters that we're going to construct. You can characterize them with the impulse, the step, or the frequency responses. And the impulse and the step and the frequency responses are equivalent ways of describing a particular filter, whether it's digital or analog. Okay. So one thing I wanted to introduce today that is new from the filter discussion in the last class is window filters. So this is a common way that you filter digital signals in the time domain. To get an idea of a window filter, or to get a sort of picture of a window filter, maybe the simplest window filter is the one we call a rolling average window filter. So in the rolling average window filter, you put into your filter your digital signal, and out of your filter comes your processed digital signal, and each sample on the output is simply an average of n neighboring samples on the input. So if it was an average of 1, you'd get exactly a copy of what you put into the input coming out of the output. If it's an average of 3, for example, so maybe the target sample and then a sample earlier in time and later in time, you get an average of those 3 samples. And you could imagine having averages of n samples, and that's your rolling average. So we make it a rolling average by dividing the sum of the samples in your window by the total number of samples. And so this is pictured here in this little equation. So the xi's are the inputs, the yi's are the outputs from the filter. And you see that we're summing a number of samples at the input. So that's the sum in the average, and then we're dividing by that number of samples. So that's the average, computation of the average. And the samples that we sum and then average, those n samples that we sum on average. If you think about a given sample I, if we're going to sample n samples around that sample I, we take that sample itself, and then we take n divided by 2 samples earlier, n divided by 2 samples later to get a total of n samples that we're going to calculate the average for. So that's a rolling average filter. So one thing about the rolling average filter is it's very good at eliminating kind of white noise or random noise. Another thing about the rolling average filter is it's not so good at separating or isolating different frequencies. So it's an example of basically when you apply a window, when you use a window filter, really the typical window is just some range of samples, say a range of n samples. Samples earlier than that are weighted by 0, so they're ignored. Samples later than that are weighted by 0, so they're also ignored. We only look at the samples, n samples in that window. A typical window filter will actually tend to weight the samples in the middle more, the samples at the ends of the window less. And it's as if you're looking at the data kind of through a window. So each time on the output, we keep looking at the data through this window, through this mathematical window, through this math window that might be simply a rolling average or a more complicated average of the data in the window. And that determines the output. So the output is really the input looked at through a window. It's really, well, mathematically, yeah, the output is sort of convoluted with this window. So beyond the rolling average, I mentioned the Hahn window, the Hamming windows. These two windows have better responses in terms of attenuating unwanted frequencies. They have less good responses in terms of removing white noise or random noise. So, you know, sometimes a rolling average filter is optimal for you. Sometimes a Hahn or Hamming filter is optimal for you, and we'll explore these. All of these filters, this simple rolling average, or this Hahn filter, or this Hamming filter, they're all basically low-pass filters. So low frequencies will get, when you do this averaging process of the samples of the input, then low frequencies are going to pass through. But high frequencies, they will tend to be attenuated. Because if you imagine the window, you're looking at the data on the input in a little window. If you've got one complete oscillation of the of a frequency in that window, when you add up the samples in that one complete oscillation, that's going to cancel out. If you've got 2 oscillations or 3 oscillations or 4 oscillations in your window, in your rolling average window or your Hahn or Hamming window, then again, those oscillations will tend to cancel each other out. So higher and higher frequencies are canceled out more and more by the rolling average or the Hahn or the Hamming filter window. Low frequencies, on the other hand, if your frequency of period is such that in the filter window, you only see a small fraction of a period, then it's not canceled out. If you're at the peak, the peak's going to come through. If you're at the trough's going to come through. If you're at the node, you get the node through. And so all of these filters, the rolling average, the Han and the Hamming, they're low frequency, low pass filters. I'm going to show you code that calculates this, that computes this. But this is just sort of a summary part of these three filters that I've mentioned. So on the left-hand side, here are the windows for the three filters. So I said in a simple rolling average, here's called a rectangular window. Each sample in the window is uniformly weighted. And so that's what you see. We've got n samples in our window, and this amplitude here is just the weighting we give those n samples. In a Han or a Hamming window, so that's this central plot here, this lower plot here, there's still a window of n samples. If you're outside that window, you're completely unweighted. If you're inside that window, you are weighted. But the samples in the center of the window are weighted more than the samples at the edges of the window. And so that's a feature of the Han and the Hamming filters. It's in a way, it's as if a Han or a Hamming filter is kind of a superposition of several rectangular filters. You got your broadest rectangular filter, then in the middle of that, you've got a narrower filter. In the middle of that, you've got a narrower filter. And by doing that, you can optimize the frequency attenuation of the filter to optimize frequency attenuation over kind of white noise attenuation or random noise attenuation. On the right-hand side here, just to show you that quantitatively, this is the kind of the frequency response of those filters. For the averaging filter, the Han filter in the center, and downstairs here, the Hamming filter at the bottom here. In the very center here, at 0, this would be a very low frequency. And so this is unattenuated by any of these filters. This very low frequencies get through all of these filters. As you go away from the 0 towards the left or the right on any of these plots, this vertical axis, these negative decibels is increasing attenuation of those frequencies by these filters. As we said, we argued that if you go to higher and higher frequencies, you get more and more and more cancellation of the oscillations of the signal in your window, whatever your window. And so you get less and less and less of that signal through your filter. And so that's what you're seeing. If you go over to the far right over here, you've got strong attenuation of any frequency, of higher frequencies, and same over here on the left-hand side. It's just showing the strong attenuation of high frequencies. You also notice this oscillation in here. This oscillation in the frequency response is simply, if you imagine that you had 10 complete oscillations within your window, exactly 10, and then you gradually change the frequency to have 11 complete oscillations in your window. At 10, you completely cancel out the input signal. At 11, you completely cancel out the input signal. But in between 10 and 11 complete oscillations, there's a small fraction of an oscillation that's not canceled out, and that gets through your averaging procedure. So you see in the frequency response, you not only see that in general terms, as you increase the frequency, less and less of the input signal gets through to the output, but you see oscillations of the frequency response with a frequency that corresponds to a period, which is your kind of averaging window, your end samples that you're looking at in your particular window.